All right, so we're going to be building polynomials. So we're going to start from this place where we're given the zeros. Right, a polynomial. So first one, the zeros that they tell us, 2, 3, and -1. That's the zeros. If there are 3 zeros, we know that this polynomial should have what degree? X to the third. 3 zeros, third power. So we know when we get done, we should have something x cubed and then something after that. Now, what the way to do this is to start with the factored form. What is the factor that goes with 2 being a 0? X minus 2, x minus 3, and then x plus 1. Okay. See what's happening here? What's happening with the signs? They're flipping. They're opposite signs. Okay, so that's the way it's going to be every time. So it's going to opposite signs. And then you need to multiply it out. So this is the factored form of that polynomial. The last what we want to do is write this polynomial in standard form, the way that we've been presented the polynomials to start with in the last couple of sections. So we need to multiply this thing out. It does not matter what order you do that in. If you want to do these two together and then multiply that answer by x plus 1, or if you want to do these two together and then multiply that answer times x minus 2. It really, or if you want to do first and third and multiply those together and then multiply by the one in the middle. It doesn't matter which order you do that in because multiplication is commutative, right? But don't try to do them all 3 at once. That's where mistakes always happen, okay? So this is the way I do it. I start with these two on the right and get that answer, and then I distribute the one that's in front. That's the order that I do it in. That's not always the best order to do, but there's times when you would want to change what order you're doing things in just to make things easier on you when you're multiplying. But it's just distributive property, FOIL method, if you've heard that before, with those two. So x times x is x squared. X times 1 is x. And then negative 3x and negative 3. And then before I multiply, I'm going to simplify. So you want to simplify as you go on this so that it's x minus 2 times x squared minus 2x minus 3. Okay. So x squared plus x came from taking x times x is x squared, x times 1 is x. Then negative 3 times x is negative 3x. Negative 3 times 1, negative 3. And then simplify that. And then the last steps here is distribute this to that. So I'm going to distribute x to all of those. And then I'm going to distribute negative 2 to all of those. So negative 2 times x squared be negative 2x squared, positive 4x, positive 6. You guys hopefully remember doing the multiplying polynomials out from right before fall break. We did that operations with polynomials stuff before fall break. That's really all this is doing that, but you're getting your information from a different place this time. And then simplify that. So x cubed negative 4x squared plus x plus 6. Now, since all the zeros that they gave us were real numbers, didn't have any i's or nothing ugly in there, how can we check this to make sure we got it right? We could do synthetic division and make sure it's zeros. That's one way. What would be another way? Well, yeah, if we factor, we might. This one won't factor by grouping, but maybe it will. Maybe that's a good idea for some. What's an even easier way than synthetic division to see what does the zero idea? What is that? What does a zero do? Plug them in for x and make sure it works out to be 0. That's true. Think about even less manual work, like, because that's the same thing as synthetic division. It would do the same thing, and it would verify them. Absolutely. If I graph this on the calculator, where should it cross the x-axis? At the zeros, at 2, 3, and -1. If it doesn't, something's wrong. If all your zeros are real numbers like this, that is definitely the best way to check, because it's y equals, graph the thing. If it doesn't cross at those spots, something went wrong. Either you missed a sign or mismultiplied or misadded at some place. So you know to go back and check. Okay, so that's always a great way to check that thing, to make sure that it does cross the x-axis at those spots. So if I did that for this particular one, I would need to open the calculator. So I'm going to y equals, and I've got x to the third minus 4x squared plus x plus 6. So we see there at -1, it's crossing. I can verify that by hitting trace at -1. I get the y value of 0, 2, not sure what happened there, but 2, enter, 0, and 3, enter, 0. So I did get the right polynomial at the end. So keep that in mind. There's ways to check. These are equations we're dealing with. So equations always have ways of checking them to make sure you've done them correctly. Let's look at another one. Say we're given the zeros 3, -3, and 4. And we want to make the polynomial that does that. What are the factors that go with that? All right. Now, again, remember, change the signs. Makes the opposite sign. The next thing to do is multiply the thing out. Now, this one, which way would be the quickest way to multiply it out? Yeah, those two are alike. They're the factors from a what? The difference of squares. That's what they're the factors of. So if we multiply those together, it should make a shorter problem, right? Because remember, difference of squares are real small. So x plus 3 and x minus 3 multiplied together, that'd be x times x is x squared, and then positive 3x, and then we have a negative 3x. So that's going to turn into x squared minus 9 times x minus 4. If we had multiplied together x plus 3 and x minus 4, we'd ended up with a trinomial, something with 3 terms to multiply something out to. We'd get the same answer at the very end, but it's more work. It's more operations, more steps. Tucker? This one, 4 should be, it's a positive 4 here, so it should be x minus 4 there. The opposite, it's always the opposite sign when you build your factors of what the 0 is. Okay, so we can shorten it up by looking for those pairs that would work out really nice for us. We can shorten up our work, and then we're just distributing. Whether we distribute x squared or x minus 4, it doesn't matter. It's the same work. X squared times x is x cubed. X squared times -4 is -4x squared. And then distribute -9, 9x plus 36. And there's nothing to simplify on that one. So there's an advantage to recognizing some pairs that go together on your factors. Won't always do that, but there's really seeing those things can make make things work faster for you. Okay, and then how can we verify that that's correct again? Graph it. Make sure it crosses at the places that they told you. If it doesn't, something went wrong. You got to go back and look. Okay, so if you graph that, it should cross at those places. All right, so let's look at this one. It's a little bit different, but still very similar. The zeros are 0, -2, and 7. Zero is a 0. -2 and +7 are also zeros. So the factored form looks like what? That 0, technically this is x plus 0 for that guy, but adding or subtract, if you put x minus 0, it's the same thing. But adding or subtracting 0 does nothing to x, right? It just makes it x. So plain x for a 0 of 0, and then x plus 2, opposite sign, x minus 7, again from the opposite sign. And then multiply it out. It doesn't matter what order you do this in. It really doesn't get any easier either way. I'm just going to do it that way. So that's x times x squared minus 7x plus 2x minus 14. And then simplify that. And then the last step's the easy one. Distribute x cubed minus 5x squared minus 14x. And there's your polynomial. So given some real zeros, that it works out pretty nicely for that to happen. Real, and then all these are integers right now, so that makes it even easier. Works out pretty good for us. Okay. All right. But remember, your degree and the number of zeros should match up. Okay. All right. Where it starts getting a little bit sticky is when they start doing this thing with the conjugate pairs. The conjugate pairs theorem says is if a radical square root is a 0, then its conjugate is also a 0. They come in pairs. The reason they come in pairs, square roots, what do we always put in front of square roots when we were using them to solve a quadratic or plus or minus? Positive is one, the negative is the other one. That's the conjugate pair. So they always come in pairs. Now, the tricky part is the fact that they're not going to tell you sometimes about the conjugate. They'll say, okay, here are your zeros. So like example D, your zeros that you're given would be the square root of 2 and 5. You've got to know that, oh, there's this other one here. There's a negative square root of 2 because the complex or the conjugate pairs theorem is you've got to know that that's there. They didn't tell us about this. But you've got to know it's there. Because if the square root of 2 is there, then the conjugate to that, the opposite, the negative. So this takes care of the plus. This one takes care of the minus for the plus or minus in front of a square root. So you've got to know that that's there. So you've got to be able to recognize that. Now, when you go to build your factors, though, nothing changes. You just got square roots in there. So I'm going to do the x minus 5 first, and then I'm going to do the 2 with the square roots. because I know I want to multiply those two together first, because the square root stuff, you want to put those together. So the factor for x, for the 0 of square root of 2 would be x minus the square root of 2. The factor for the negative square root of 2 would be x plus the square root of 2. Still changes signs. That's all it does. Okay. All right. Now, the things with square roots we want to multiply together first, because they're alike, right? They've got square roots in them. And here's what's going to happen when we multiply that together. The square roots are going to go away. Magically. Not magically. Mathematically, they're going to go away. There's no magic in here. Now, the way it works is the same way that it's always worked. You distribute. X times x is still x squared. X times the square root of 2 is x square root of 2. Okay, so that's distributing x to both of these. And then I distribute a negative square root of 2. Well, negative square root of 2 times x is negative x square root of 2. And then, what's negative square root of 2 times positive square root of 2? 2. But not just 2, but negative 2. So x, or negative square root of 2 times the positive square root of 2 is negative 2. Or negative, or you could think negative square root of 4, but we know the square root of 4 is 2. Okay. What happens to those middle pieces, Nick? They cancel out. That should happen every time. Okay. And you have x minus 5 times x squared minus 2. And then you need to multiply it out. X times x squared is x to the third. X times negative 2, negative 2x, negative 5x squared, plus 10. Is that in the right order? No. You need to put it in descending order. So x cubed minus 5x squared minus 2x plus 10. Can I still check it with the graph? Yeah, square root of 2 is a real number. So if I graph that with the calculator, x to the third minus 5x squared minus 2x plus 10. We know how to check 5. That's the easy part. But we want to check square root of 2. You can do that with the calculator as well. Hit trace. And then, whoops. Go back to your graph. Hit trace. And then hit second square root of 2. And it converted it to a decimal, but the big thing here is y equals 0. Yes. So we definitely got the right polynomial at the end. So you can still check it. As long as your zeros are real ones, you can check them with the graph and the trace function. Okay. All right. Let's do another. Here are your zeros. 4 and 1 minus the square root of 5. Which one did they not tell us about? 1 plus the square root of 5. Oh, this is there. Okay. They didn't tell us about that one, so we've got to bring it to the table because they're not going to tell you about it. Now, when you set up your factors for one of these, it's no different. What's the factor for the 4? X minus 4. Now, if it was 1, your factor would be x minus 1, right? But it's 1 with a minus square root of 5 and 1 with a negative with a positive square root of 5. So when you set that factor up, it's going to be x minus 1, and then one of them has a minus the square root of 5 and one has a plus the square root of 5. The number that's in the front, if it's whatever it is, do the opposite of it for your sign in the middle. And then one's a plus and one's a minus on your square root part. That's the simplest way I can explain that. I was thinking about that on the way to work this morning. How am I going to explain that in a way that doesn't cause confusion? And that's what I came up with. So it may not be the best thing in the world, but that's what I came up with. All right. Now, which two do you think you want to multiply together first? The ones with the square roots. Now, that's ugly. It's long. There's nothing we can do about it, but just do it. Okay? The old Nike slogan. They don't use that anymore. Hey, come on in, Miss Peggy. That's okay. All right. So
Elizabeth needs to report to the office.
okay. All right. So distributive property, one piece at a time. Don't try to do too much at once. Okay? Because that's where you can make a lot of sign mistakes and a lot of issues. So x to everything there. So x squared minus x plus x to the square root of 5. And then minus 1 to everything in there. And I'm going to stack it like I did back when we were doing polynomial operations. So that'd be negative x and positive 1. And then a negative square root of 5. And notice I didn't put it underneath here because it wasn't a like term with that. Let's put it out here. That's okay. Thank you. All right. And then the negative square root of 5 to that stuff. So that'd be a negative x square root of 5. And then a positive square root of 5. And then a negative square root of 5 times square root of 5. Square root of 25. Square root of 25 is 5. So I can put that under there. So just trying to stack up like terms. Okay. So I'm just going to put parentheses around that. We know we got x minus 4 still to do. Now, if I simplify all this, x squared is going to come down. Negative x and negative x, negative 2x. What happens to the x radical 5s? They should. Anything that's got a square root should go away when you multiply those things together. Okay, keep that in mind. And then negative square root of 5 and positive square root of 5 cancel each other out. And then we have 1 minus 5, which would be negative 4, right? So anytime you have square roots in your zeros, they should cancel out when you go to multiply out the factors. The square root should go away. Same thing's going to happen when we have complex numbers in there. The I should go away at the end. Okay? Now, distribute x times x squared, x cubed, minus 2x squared, minus 4x, and then distribute negative 4, negative 4x squared, positive 8x, positive 16, x cubed, minus 6x squared, plus 4x, plus 16. Is it pretty? No. Is it long? Yeah. But should turn out to be. And you can still check that with the graph because the solutions were real. 1 plus the square root of 5, it's a decimal number. We know that. So you can check that with the graphing calculator and the trace function to make sure that that works. Okay. All right, let's do a complex one. Four, 3, and 3 minus I. These are, I didn't write zeros there, though. Zeros. Those are the zeros they give us. Which one's there that we don't see? 3 plus I. Good, yay. Okay. Not given. Okay, we got to remember to put those in there. Now, what should the degree of this thing at the end be? What x to what power at the end? 4, because how many zeros do we have? 4. That always matches up. Never is that different. Okay, so set them up. What's the factor for 4? X minus 4. The next one is x minus 3. And then the next one would be x minus 3 plus I, and then x minus 3 minus I. It doesn't matter what order you write those in. If you wrote x minus 3 minus I first, that's fine. It doesn't matter. Now, which two go together first? The i's. Okay. Same length and same lot of work as the ones with the square roots. Okay. But the only thing we've got that's going to help us is the fact that what does I squared turn into? Do y'all know? This from we're talking about. I squared is -1. So if we multiply I times I, which we will at some point in this, I squared changes to a -1. Keep that in mind. That's the reason it does that is because I is the square root of -1, and if you square both sides, it gets rid of the square root, and that's -1. That's where that's coming from. Okay, so we're going to multiply these two together. X times x, x squared minus 3x minus ix. Let's get the x to everybody, and then get the -3 to everybody. So that's a -3x, a positive 9, and then a positive 3i. And then I times x is positive ix. And then I times -3 be -3i. And then positive I times negative I is negative I squared. What we've got to know is that when we do that, I squared is really -1. So it makes it a like term with that 9. Okay. Simplify from there. So x squared comes down, -6x. What happens to everything that's got an I? They cancel out. The only thing that stays in there is the I squared. Treat it as -1. So we have 9 minus -1, which would be plus 10, right? All right. It's a positive 9 and it's minus -1. I squared changes to -1, so it's a minus a negative. Double negative makes positive. Hey, yeah. Right. Correct. All right. Now, this is where you got options about how you go about doing that. If you want to multiply these two together first, you can. But at the end, you got to multiply it all together. It doesn't matter. It's the same number of steps no matter which way you do it. Okay. I honestly think it's easier just to multiply these two together and then get that trinomial and say trinomial times trinomial. Because then you only have that one last step to do after you've done that. So if I multiply these two together, that's x squared, and this is something pretty familiar with us. So we could probably do some of this in our head. So x times x is x squared, and then I've written stuff on my screen. It's not up there yet. That's not a good sign. X times x is x squared. -4 times -4 times x is -4x, and then we got a -3x, so that'd be -7x in the middle, and then a positive 12 on the end. And I'm writing this up here, but you guys can't see it. It's awesome. It's slowly getting there. So these two multiply together to be x squared minus 7x plus 12. It's multiplying two binomials together. And all right, so we got x squared minus, there it is, 7x plus 12. And then x squared minus 6x plus 10. We got three distributive properties to do, and maybe this will work. So let's do that. So x squared times x squared, there's our x to the fourth power. X squared times negative 6x would be negative 6x cubed plus 10x squared. And then I'm going to run the negative 7x through. Be negative 7x cubed positive 42x squared negative 70x. And then run the 12 through there. 12x squared negative 72x, and then positive 120. I've stacked it up so I can get like terms easily. Bring it down. X to the fourth, 13, negative 13x cubed, 52 and 12 be 64. 72 and 70 will be 142 negative. Yeah, the 10 up top, yeah. You get it. And there's our polynomial. Now, can we still check this with graph? Part of it we can. Okay. Now, the complex solutions can't be checked with trace. But what's the probability that you multiply this out and 4 and 3 work and you got the wrong one? Not very likely. That the end polynomial you end up with, 4 and 3 should work in it. If it does, great. It's not very likely that you got the right polynomial at the end and it doesn't work if the two real ones work or the real solution works. Okay. Now you could check the 3 plus I and the 3 minus I with synthetic division. That's not exactly easy, but it's doable to check that. But it just, I think checking the real ones with the graph, you also should know the graph will only cross the x-axis at the real ones. It doesn't cross at the complex ones. They don't show up on the graph. That's one of the reasons you can't check it with the graph. Check that part of it with the graph. But the real ones do show up, so you can always check those. Okay. All right. So this is what we're going to work on the rest of today. I think it's page 384. Check and make sure. Page 384, number 20 through 31. I know that's not a lot of problems. I'm sorry. It's a joke. These do take a while. So 11 problems is more than enough to get you started. I would start on some of them today, and then on Monday work on the rest of them. Some of them you can get down to, like 28, 29, 30, 31. Those have a lot going on. So definitely a lot going for that. Plan of attack for the next